Welcome back, engineers. In this video, let's look at the next topic in our system design core concept series, and we're going to talk about containerization. I hope you're ready. Let's get started. So before we get into what is a container, what is containerization and how it works and all that, let's try to understand what is the problem that we are trying to solve here. So the problem is called "it works on my machine" problem. So if you have ever been in a development team, you might have seen this situation where one of the devs are saying, "it works on my machine C," and he or she is showing the laptop and the code actually works there. And then on the other side, when the same code is being run on some other machine, maybe at a machine of a QA person or a project manager or even the client, it does not work there. And they're saying, duh, it needs to work on mine too, right? And this is a very classic situation. And trust me, I've been there on both sides of this equation, and sometimes it's very funny, sometimes it's embarrassing, but overall it's not really pretty. The code is supposed to work on any machine, right? Because it is the same source code. So why does this happen? Why does the same source code works differently on different machines? Because if it is the same set of lines of code, it needs to perform in the same way, right? But it doesn't. So let's try to understand what does it take to actually run a code. So what does it take to run code, right? So as you can see here, it is not just the source code that is required, but there are a lot of other things around the code that are required to be running in cohesion so that our application runs, our code runs, right? So let's try to understand this list. So first on the top of the list are core system resources. So for running any kind of application, we need some kind of a compute, either a CPU or a GPU and so on. And then we need a RAM where we can hold our variables and the current state of the application and so on. And then we need disk if you are dealing with file reading or writing and so on. And then we need a runtime environment, right? So this runtime environment consists of an operating system on which our application will be running. And then we need some kind of a language runtime. So if you're running Java based applications, we need Java runtime environment. If you're running Node.js application, we need a Node environment. If you're running some front-end applications, you might need the browser environment. So we need some kind of a runtime environment. And then we might also need some system libraries, right? So maybe you're trying to make some network connections. You will make use of the system's built-in libraries to handle the network connections and so on. So these are the runtime environment things that are required in order to run the code, right? And finally, we will look at the app-specific needs. So for running the application, we obviously need the source code. This is the set of instructions that the application is trying to use, and that is how the application works. And then we need some kind of third-party libraries. So the third-party tools actually help us because they have tools and libraries necessary for things that are already solved, maybe some database layer, maybe some encryption layer and so on. So we can directly use them so that we don't have to write those code ourselves, and that's where we can use third-party libraries. And for third-party libraries, there can be production level dependencies or development level dependencies. So some libraries help us build the code, some libraries help us run the code at production, right? So depending on the needs, we use different types of third-party libraries. And then we have environment variables. Again, environment variables can be different for production or dev or QA and so on. So depending on the need, we can change our environment variables, which in turn change the behavior of our application because maybe they are connecting to a different database, maybe they are using a different configuration file and so on, right? And then we need some kind of configuration files. Maybe to run tests, we can use some kind of a just.config. Maybe we can use some kind of webpack.config. So there can be different config files that are enabling the application to run in different contexts, and this is how configuration files can help us. And then we might also need some static assets, maybe some icons or images or some other files that are very static in nature and they don't change, and those are helpful in running the source code. And among all these, there are some things that we can control as developers and some things that we cannot control. For example, if you're looking at third-party libraries, we can control the library that we're using, and we can know the exact version of the library that we need for our application's current state, right? But we cannot control the third party that is actually building and maintaining this library to push new updates, right? So if they are pushing new updates and those updates are actually coming into our application, it might break our application, right? And we don't have any control over it. So we need some kind of version control mechanism or version locking mechanism so that we don't fall victim to those breaking changes and so on. And obviously this app needs list is non-exhaustive, so there can be different needs depending on the application and the complexity or the scale of the application, right? So the whole takeaway is that it is not just the source code that is required to run the source code. There are so many things around the source code that are in play, right? So this is an entire ecosystem, not just the source code. We need some kind of a compute, we need some kind of a runtime environment, we need the environment variables, we need the static files. So everything working together are making the app run or the code to be running perfectly, right? So because of all these, I can have different versions of some of these. I may be running the code on a different OS than you. I may be using a different runtime than you. I may be using a different third-party library version than you. And because of all this, the app behavior changes from system to system. And before containerization, this was a huge problem. And the containerization concept solves this problem by wrapping everything that is required to run the code into one little box and create that little ecosystem which can be shipped everywhere to different machines. And because the ecosystem is built with everything that is required for that application to run, it works exactly the same way on any machine, right? That is the whole idea behind containerization. So the concept of containerization is solving this problem. It works on my machine problem, right? So let's go into the details now. So what is a container? So you might have heard this term a lot of time. People keep talking about Docker containers. So what is a container? So we can think of container as a shipping container. We must have seen this at shipping docks and so on. So this is just a box, right? It's an empty box which can be holding certain things, and this can be shipped anywhere in the world. So we can put anything that we want in this. As you can see here, we can put boxes of so many things and they can be shipped to anywhere in the world. So whatever we need, maybe we need some kind of libraries. Maybe we need files. Maybe we need some installation instructions. So there can be anything that is required to run the code. We can put them in our container, and this container will become our ecosystem, right? So because this is an ecosystem that is consistent, we can ship it to any system that we need, any laptop or any production environment or different environments, and it will run exactly the same way. So this is what container means. So it's like a virtual box that is holding all the things that we need to run our code, right? So you must have heard this term virtual machines, right? If you have ever used tools like VMware, Fusion, or VirtualBox and so on, so they use the concept of virtual machines. But containers are different than virtual machines. So let's try to understand this key difference. So let's say we have a Mac OS like this, and we are running some kind of a virtualization software like VMware Fusion. So because of this, we can run different operating systems on the same host machine. So this host machine is holding a Mac, right? And here we are able to run Ubuntu here, and this is Windows 10, and this is Windows 7, and so on, right? So the same host machine is able to launch different operating systems, and inside this I can do operating system specific things. So if I'm running some .exe files, I can run them here inside Windows virtual machines. So it's important to understand that this is not container, right? This is not a container. This is an entire virtual machine. So what is a virtual machine? Let's try to understand the differences. So one of the first differences is usage of resources. So in a virtual machine, there is an entire operating system that is copied, booted, and loaded inside the host machine, right? So that operating system will have its own kernel, its own dedicated RAM, its own dedicated disk storage, and so on. And it is an entire computer in itself which can be booted and run independently. But in the case of a container, it is sharing the kernel with the host, sharing host kernel. So if you don't know what a kernel means, it is the link between the hardware and software of any computer, right? So containers are not entire operating systems copied onto different boxes. They are just lightweight application software that are sharing the host kernel to make use of hardware resources, right? So that is the first difference. Second difference is startup speed and size. Because the VM needs to boot up the entire operating system, this one is slow. But in the case of container, this is extremely fast because there is no boot up involved, and because of this it is extremely fast and it is nearly instant to launch any container, right? And then the third important difference is isolation level. So in the case of a virtual machine, we are getting hardware isolation. Okay, it means that that virtual machine will hold its own hardware virtualized from the host system. It has its own CPU, RAM, and so on, and it is not shared between the host computer. But in the case of a container, we are getting process level isolation. We are still in connection with the host machine and we are getting process level isolation. So there is a trade-off here. Do you need complete security? Then we can go for a virtual machine. So this gives us a lot of privacy and security. But if we need something light and fast, then we can go for a container. So that is the key difference between a virtual machine and a container. So if we want to run our code that is independent of any host operating system, we can make use of containers. But if we need any specific operating level features or we need specific security and privacy features, we can go for virtual machines. So these are the main differences between containers and virtual machines. Now let's talk about Docker. So Docker is a company that kind of mastered this concept of virtualization, and they have created the necessary tools to containerize any application, which means to build the entire ecosystem for any application, and then they made it lightweight and simple for anybody to use, publish, or ship it anywhere and run it anywhere. So what they have done is they have built something called a Docker engine. So this engine will make the entire Docker ecosystem to work together so that our job as development teams become easier, right? So let's see what are the things that are involved in this ecosystem. So these are some of the key terminology that we need to know when we are dealing with Docker ecosystem. The first one is the Dockerfile. So this Dockerfile is like the recipe. So what is a recipe? So for cooking any dish, we need the set of instructions and the things that we need, right? The ingredients and the set of instructions. So that is provided by Dockerfile. So in our application example, it is the list of asset files that we need, list of instructions that need to execute one step after the other to run the application. So this is simply a text file. It does not do anything. It just lists the things that we need. And using this recipe, we can make our meals. So this is like pre-cooked meals, right? So all the things that are required from the recipe, we have pre-cooked and made it ready. So this is not the exact dish, but this can be used for building out dishes. So any Docker image will go through the Docker file for the set of instructions and prepare itself to be launched. And when we launch it, we launch containers. So these are the exact boxes that we have seen before. So this we can launch multiple containers like this using the same image. So the Docker file gives us the set of instructions, image is carrying all the pre-cooked stuff that is required to run the code, and the container is the actual instance where the application code is running, right? So these are the key main building blocks of any Docker application, right? So there are some other things around this that we can look at now. First thing is the registry. So this is like the GitHub for Docker images. So if you have built something that can be reused, you can push it to the registry so that other people who want to use the same image can pull it and launch their own containers, right? Let's say you have an amazing recipe and you can build images with it and push it to the registry so that anybody else can use it, right? The same recipe can be repeated. So this is one of the main advantages of containerization, which is the concept of portability. Right, so you build the image once, you can take it anywhere and you can launch containers using that. So registry is the placeholder for all the public images which anybody can pull from or push to, right? And then we have Docker Scout, which is responsible for security scans. So inside the image, if there are any security vulnerabilities, we can use Docker Scout to make those scans and improve our images for security reasons. And there is one more file called docker-compose.yml, which is like a superset of different Docker images. So if you're dealing with multiple Docker files and images, we can give those instructions in docker-compose.yml, so that we can give things like, so first this Docker image needs to be run, and the image below that is dependent on this first image, and so on. So we can create that dependency chart using docker-compose.yml. We can also give things like external port mapping. So if we want to expose the internal container to the host system outside, we can do that port mapping here. Do you want to share some network or any volumes or disk volumes between different containers? We can also do so by configuring it in the docker-compose.yml. So this file is actually orchestrating different Docker files within the same application. So we are still in the same ecosystem. We are just using different Docker images for different needs, right? So these are the key concepts of a Docker ecosystem. Now let's take a look at Docker Desktop and understand all these concepts. So the Docker Desktop is an actually useful user interface that gives us all the tools that we spoke about and makes it easier to manage them, right? So for example, let's look at builds. So we spoke about the Dockerfile, which has a set of instructions, right? So when we first build some image, the actual Dockerfile stays here and we can go inside, and if we go through the source code, we can actually see the Dockerfile source of instructions. So this is the recipe file for building the image, right? And then when we go to images, we can see all the images that are being built using the Dockerfile. So these are the pre-cooked set of recipes, and then we can launch them using this simple play button. So we can launch any number of containers for the same set of image. So this gives us the flexibility of portability. We can launch multiple containers and they will all run with the exact same ecosystem, right? So for example, I have launched this once. I can click on it again and launch another container using the same set of instructions, same Dockerfile instructions, same images. And if we go into containers, we can see that there are multiple containers being run using the same image, right? So containers are the actual runtimes which are actually running the code. And then we have volumes, which is the disk storage. This can be shared between containers or used by any containers by themselves, right? And then we have Docker Hub. Docker Hub is where all the images are being hosted, which can be used for different people. For example, let's say somebody is maintaining the Python image. So they will work on this image, they will try to build features on top of it, and anybody else can just simply do a pull and then they can run it, right? So this is how the Docker Hub ecosystem works, and anybody can push images to it. For example, if I want to push this image, I can just go here and I can say push to Docker Hub, and other people will be able to use it. So this gives us great flexibility. And then we have Docker Scout. Docker Scout is responsible for analyzing security vulnerabilities and issues within images. So let's say I have an image here and let's analyze this. Let's give it a minute. So the analysis is done. We have a couple of issues. We can go inside this and we can see that there is a high severity issue and there is a low severity issue. We can open this. We can see some more details and we can click on this for more details, and we can go through the website where there are details about that particular vulnerability. So here in this case, there is some issue related to regular expression denial of service and so on, right? So we can further go through them and improve our image so that we can reduce our dependencies, right? So that is about Docker Scout. And then we have extensions. This is just like the plugin ecosystem, which will enhance the usage of our Docker desktop application. So we can use these plugins to add additional capacities or capabilities to our Docker desktop. Now let's go to VS Code and see one of the code repos that we have been using for our demos. So this is the API gateway demo, if you remember. So we have used multiple folders, and there are different services: order service, product service, user service 1, user service 2, and so on. And then each folder will have its own Docker file. So if we go here, this Docker file will be the recipe book. So this recipe contains all the instructions that we need to run this image. So we are saying that it needs Node.js runtime, and it needs the app folder. It needs to copy all the contents from package.json, and then we have an instruction saying npm install, which will install everything from package.json, and then we'll copy the source code. We are exposing the port, and finally we will use node command to run the application. So this file will not do anything. This is just the recipe book. So if we issue the command docker build using this file, we will create an image that will pre-cook all these set of instructions, and using that image we can actually launch the containers, right? So this is how one Docker ecosystem works, and we have multiple Docker files like this, and our entire application is dependent on all these Docker files to run. So that is when we use docker-compose.yml, because we are orchestrating the communication or the deployment between different Docker containers and communicating with them, between them, right? If you look at the docker-compose.yml, we have 4 different services: user service 1, user service 2, product service, order service, and these are being built one after the other using the respective folders Docker files. So user service 1 will use the Docker file from this folder to build itself, and it will expose the port 3001. Similarly, the other services. And once all of these services are launched, we can launch our main service, which is the API gateway service, which is using nginx image, right? And this will be exposing port 8080, and it depends on all these 4 services. So docker-compose.yml can be used to create these dependencies. So this API gateway will not be launched unless all these 4 services are up and running, right? So that's how we can use this. And we can also create the different networking or storage systems that are responsible for running this application. So in this case, we are creating a dedicated volume which will be using the configuration file nginx.config, and the application will make use of this config file to run, right? So that is all about docker-compose.yml, Dockerfile, how builds work, and so on. And then finally, let's look at some essential commands to work with this Docker ecosystem. So first in the list is docker build, which will use the Docker file to build an image. And then we have docker run, which will actually run the image into a container. And then we have docker push. This will push the image to a Docker Hub registry. We have docker ps, which will actually monitor the state of the containers. And then we have docker compose, which will be used for launching the docker-compose.yml files, and the whole system with multiple Docker containers will be orchestrated using this command, right? So these are some of the essential commands to be working with the Docker ecosystem. So that's all I had for this video, guys. I think this is all that we need to know about the Docker ecosystem. So please let me know if you have any other questions about this concept of containerization or the Docker ecosystem. I'd be happy to help in the comments. So please leave a like if you found this helpful and you have learned something. Please subscribe to the channel if you haven't done already, so that you don't miss out on any of these videos. Thank you so much for watching. I will see you in the next one. Cheers.